Hello, everyone. Welcome to ILTA Physics online problem solving lecture. Today, we're going to study one of the core concepts of mechanics, equilibrium. We often use the phrase staying balanced in our daily lives, but in physics, equilibrium refers to a state where the net force, or the total vector sum of forces, acting on an object equals zero. Imagine a person walking on a tightrope, just like in the picture below. The rope sags downward because of the person's weight, yet the person stands there without falling. At this moment, the force of gravity pulling downward and the tension from both sides of the rope are perfectly balanced. This is the state of equilibrium that we want to analyze kinetically. In other words, you can think of equilibrium in physics as a state where all the forces applied to an object match up perfectly to create a complete balance. To solve these equilibrium problems, we need to break down the forces acting on the object. Depending on the coordinate system we set up, we generally decompose the forces into vertical and horizontal components. Then we calculate based on the fact that the sum of the forces in each direction must be zero. Now let's briefly summarize the key points of equilibrium. Generally, when we think of equilibrium, we picture an object staying still and balanced without moving in any direction. This is called static equilibrium. However, in dynamics, this concept is expanded. An object moving at a constant velocity is also considered to be in a state of equilibrium. This is because constant velocity implies there is no acceleration, meaning the net external force acting on the object is zero. This is called dynamic equilibrium. According to Newton's first law of motion, also known as the law of inertia, if the net force acting on an object is zero, the object is in equilibrium and tends to maintain its state of motion. To put it another way, if an object is at rest, it will continue to stay in static equilibrium. If an object is moving at a constant velocity, it will continue to stay in that state of dynamic equilibrium. Both of these states are defined as equilibrium in mechanics. When solving problems regarding the motion of an object in equilibrium, we often start with the fact that the acceleration is zero, which means the net force must also be zero. Specifically for problems involving the equilibrium of forces on a stationary object, called static equilibrium, you can break the forces into horizontal components, the x-axis, and vertical components, the y-axis, and set up equations where the sum of the forces in each direction equals zero. Alright, let's try solving some simple problems regarding equilibrium. Problem number 1 is a very basic problem about the equilibrium of forces. As you can see in the diagram, two ropes are fixed to a wall. A small, light ring is being pulled downward at a 30-degree angle relative to the horizontal with a force of 100 newtons. Specifically, the two ropes fixed to the wall form a right angle, and the forces of the three ropes are in equilibrium. The goal is to find the force or tension exerted on each rope. As explained before, if the motion of an object is in equilibrium, the sum of the forces, the net force, acting on it is zero. In a two-dimensional plane, the sum of forces is calculated as a vector sum, where the forces in both the x-axis and y-axis directions must be zero. It's much easier to solve this if you draw a free body diagram, like the one on the right. In this specific case, the horizontal force is only acted upon by tension T1, and the vertical force is only acted upon by tension T2. First, let's look at the equilibrium in the horizontal direction. The horizontal component of tension T3, which acts at a 30-degree angle downward, can be calculated using the cosine function. The result is 86.6 newtons. In the same way, to achieve equilibrium in the vertical direction, the upward tension T2 must equal the downward sine component of tension T3. Therefore, tension T2 will be 50 newtons. This is a simple problem, but please practice setting up free body diagrams to solve it. Problem number 7 is the same type of problem as the tightrope walker we saw earlier. A person weighing 560 newtons is lying in a hammock that is fixed at both ends. The ropes of the hammock make angles of 45 degrees and 30 degrees with the horizontal. The question asks us to find the tension in the ropes for each direction. Since the hammock is in static equilibrium, the net force acting on it is zero. This means the net force in both the x-axis and the y-axis directions is zero. I will explain this problem using a more systematic method. First, to solve any problem in physics, we must decide on a coordinate system and an origin. Since this is motion on a plane, we'll set up a Cartesian coordinate system. Following standard directions, we'll define right as the positive x direction and up as the positive y direction. Usually, it's most convenient to set the origin at the object's location. Now let's draw a free body diagram for this equilibrium state. There are 3 forces acting on the hammock, 2 tensions acting diagonally to the right and left, and the force of gravity acting vertically downward. Let's start with the equilibrium in the horizontal direction. Because the object is in equilibrium, the sum of all horizontal forces, the vector sum considering both direction and magnitude, is 0. Now let's add up all the horizontal components of the 3 forces acting on the hammock. Since tension T1 is acting toward the upper left, its horizontal component is minus T1 times cosine 45 degrees. It is very important to realize that this value is negative. Based on our coordinate system, right is positive. Since T1 acts to the left, it takes a negative value. Using the same method, the horizontal component of tension T2 is T2 times cosine 30 degrees, and this takes a positive value. Finally, the horizontal component of the downward gravitational force is 0. Since the hammock is in static equilibrium, the sum of these 3 horizontal forces equals 0. Now this is our first equation. Next, let's look at the vertical equilibrium. Both tension T1 and T2 are acting upward, so we can find their magnitudes using sine functions, and both will have positive signs. The vertical component of gravity acts downward, so it has a negative value of 560 newtons. This is our second equation. If we set up the equations and solve the 2 relationships simultaneously, T1 is calculated as 400 newtons and T2 is 502 newtons. We've just solved a basic equilibrium problem using simple force decomposition. The key here is to accurately understand the positive and negative signs of the forces based on the coordinate system you've set. If you understand this principle, you can solve even the most complex systems step by step. That's it for today's lecture. Great job, everyone. I'll see you next time.